Hello and welcome to this video on momentum. Specifically, we're going to talk about what is momentum, how do we calculate it, and how does momentum work within a system. A long time ago, we talked about Newton's three laws of motions. They're on the screen here. An object in motion will stay in motion, and an object will stay at rest unless acted on by an outside force. This is typically referred to as inertia, and we haven't done much with it. The other two, the acceleration of the object, and for every action there's an equal and opposite reaction, we have done a lot with. This is almost the entirety of the forces unit, and this is part of the forces unit, though it has come up every so often since. Today we're going to focus on the first law. An object in motion will stay in motion, and an object at rest will stay at rest unless acted on by an outside force. This idea of inertia, the tendency for an object to keep doing what it's doing, is often also referred to as momentum. To get a little more specific, momentum is a measure of the tendency of an object to stay in motion. You often see or hear the term momentum is mass in motion, which means it depends on how fast it's going and what the mass is. The equation for it is fairly simple. P, which is the stand-in for momentum, equals m times v. You'll notice I'm using the little vector hats here. This indicates that momentum depends on direction. An object heading to the right does not have the same momentum as an object with the same mass heading the same speed up. Direction matters. Further, momentum is mass times velocity, which means it has units of kilograms times meters per second. This does not have a particularly useful shorthand. There's no Newton, so to speak, here. Nothing this simplifies down to. It's just kilograms meters per second. So let's take a look at this. How does this work? How do we calculate this? Here we have objects. The first is this box heading up, this 4.5 kilogram box heading up. This second is this blue one heading to the right. The final is this red one heading up and to the right. And all you need to do is just use your new equation. P equals m times v. Now remember, these are vectors, so direction matters. Go ahead, give them a try on your own. If you've gone through and done this math very carefully, you should get the following values. For the green box, you should get 9.0 kilograms meters per second up. For the blue box, you should get 2.0 kilograms meters per second to the right. And for the final one, you should get 12.5 kilograms meters per second at 30 degrees north of east. This final one is the one that we're going to focus on for a second because much like when we were talking about velocities or forces, we can also break this up into components. If we look at this as instead of north, east, southwest as an x and y, we talk about the momentum in the y direction and the momentum in the x direction. In other words, the component in that direction. The total momentum we've already said is 12.5, but if I want to find the momentum in the x direction, well, we have a triangle here. And px is on the adjacent side to the angle, and the momentum's heading this way, which would be the hypotenuse. Adjacent and hypotenuse is cosine. Cosine of my angle equals adjacent over hypotenuse, or in this case, cosine of my angle equals px p, which means that my px in this case is going to be p times cosine theta, or 12.5 times cosine of 30. Go ahead, grab my calculator, plug that in. I get a momentum in the x direction of 10.83 kilograms times meters per second. Go ahead and try py on your own. If you went through and were careful with math, you should get 6.25 kilograms meters per second. Now, we don't want to just talk about the momentum of a single object. Sometimes we'll refer to the momentum of a collection of objects. For instance, if we go back to these original objects here, I could talk about the momentum of the three of them together. The total momentum of the system of objects, the system being these three objects here. And in order to do that, all we need to do is add up all the momentum in the y direction and all the momentum in the x direction to find my total momentum. It's adding vectors, except the vector we're adding in this case is the momentum vector, not a vector of newtons or velocity. So, for instance, the green box here has a momentum of 9 kilograms meters per second up, which means it has an x momentum of 0. The blue had 2.0 kilograms meters per second in the x direction, and in the y direction, it was 0 kilograms meters per second because it wasn't moving the y. The red one we broke up on the previous page, 10.83 in the x direction, 6.25 in the y direction. And these are the total momentums we found previously. Here, we're just going to add all of our x's, so work across. 0 plus 2 plus 10.83 gives me 12.83 kilograms meters per second. In the y direction, 9 plus 0.6.5 is 15.25 kilograms meter per second. And to get the total, we can't just add 9, 2, and 12. What we need to do is draw out our triangle. In this case, I'm moving 12.83 in the x direction, and then up 15.25. Had I drawn each of these individual vectors out, starting with green going up, then blue over to the right, then red up and to the right to finish this off, I would have gotten the same result, but we can't always solve this graphically. Regardless of how you get there, this is your net result. And now we need to use the Pythagorean theorem to solve it all the way through. A squared plus b squared equals c squared, and our angle from tangent inverse. Let's go ahead and do that really quick. Okay, if you did all that carefully, you should get 19.94 kilograms meters per second at 49.92 degrees counterclockwise, which is what I'm calling my x-axis here. One more for you. Two cars are traveling as depicted in this image. What is the total momentum of this system? If you did this carefully, did all the math, you should get the two vectors add together. The total momentum is 23.26 kilograms meters per second at 25.46 degrees above the horizontal positive x direction. Depends on what your coordinate system here is. The reference angle is though 25.46. Calculating momentum, again, isn't that hard. You just have to use everything you know about vectors, which might be a little bit of a refresher. Anyways, thanks for watching. Have a good one.